energy stored in magnetic field. Now this is the part which we had already seen in case of inductance. Now this was the inductor, alright, and this was the rheostat, battery, key, and the circuit. Alright, work done by charge dq against back EMF of inductance L is W is equal to half Li square. Now that is the work done. Alright, now this formula we have already seen. Now let's try and understand a bit about it. Now see, we know that the inductor which is there, it generates back EMF whenever current flows in. Whenever current flows in, it generates a back EMF. So if it generates back EMF, then it is doing some work. And if it is doing some work, then it has some energy stored in it to do work against the current to generate back EMF. Now that work is stored in inductor in form of this half Li square. I obviously we know is current and L is inductance, and U we represent for energy, so UB. Alright, so this is for magnetic field. Okay, energy stored UB in magnetic field is this. Alright, so this is there. Now let's get back to capacitor. Now we know capacitor are two plates. This is capacitor and this is battery. Capacitor, you know, both the lines are of equal length, and in case of battery, you know that one which is small is negative, big is positive. Now let's find out what is the energy stored by a capacitor. During process of charging, Q is equal to charge on capacitor, V is potential difference between the plates, alright, and this formula is for capacitor. Q upon V is the formula for capacitance, alright. So work done by transferring charge between plates is given by half Q square over C. This is in capacitor chapter. Alright, so half Q square over C. Obviously, we know Q is charge and capacitance is C. Okay, so that also is equal to half CV square. Alright, because we know this Q is equal to CV. So Q is CV square. We know that Q would be CV. So it would be C square V square divided by 1C. So it would be 1C would get cancelled in numerator. So it is half CV square. Alright. It's also is equal to half QV. Similarly, we can again substitute those values and we can check it out. Alright. So it would be half QV. So these again are the formula which you have got to keep in mind. This is for energy stored in case of inductor. This is energy stored. In fact, these are energy stored formula for capacitor. This is the work which is stored, or rather I would say work is energy. So this is the energy which is stored as electrical potential energy UE in capacitor. Alright. So let's compare both the formula. Magnetic field energy stored is this. Capacitor energy stored is this. Alright. Now energy stored per unit volume. So energy stored per unit volume would be B square upon 2 mu 0. And energy stored per unit volume is half epsilon 0 E square, where mu 0 is permeability constant, E0 is permittivity constant, E is electric field and B is magnetic field. Again, I repeat that these are the formulae which you have got to keep in mind. Now this is about energy stored in magnetic field, alright, and this is energy stored in capacitor. We also call this as energy density. So whenever you get in a numerical energy density, these are the formulae which you have got to apply. Alright, okay. Now let's talk about energy density of a magnetic field. Now again solenoid and current carrying coil. Now this is cross and this is point. Now point itself means it is coming out and going down like this. So it is going down like this round the tube. All right, that's what is solenoid. All right, so going like, so that's what has been designated over here by dot and by cross. Dot is when lines of force are coming up like this, and going down is this. All right, so it's going like that. This is the length of the solenoid again, and the magnetic field generated owing to these coils circulating around the tube is B. All right, which is here B. We know here we are not concerned with, because there's out, and these two sides also, whatever magnetic field generated cancels each other, and this is out, so it doesn't generate any field inside. So we are concerned about this. All right, so UB is energy stored within the volume AL. Now volume is AL, we know area of cross section into length is volume. So energy stored per unit volume would be, formula we had seen of UB, formula we had seen for energy, that is divided by volume. So it becomes half Li square into 1 over AL. So I have also mentioned it over here. So this is it. All right, so what happens is you get UB is equal to L over L, capital L, that is inductance over length, I square, this I square remains, this 2 is this 2, A. So this is equal to energy stored per unit volume in magnetic field. So energy stored per unit volume in magnetic field. All right, so this is UB over AL. What we get is UB over AL. Now we already derived that L over L is mu 0 n square A for long solenoid, inductance per unit length. We had seen that small n is equal to capital N over L. This is number of turns and this is number of turns per unit length. This is just to recap. All right, so just to recap about this so that you don't have any confusion. So this is number of turns per unit length into area. So what do we do? So we, instead of L over L, we substitute mu 0 n square A, and this part which is there, I square over 2A, remains as it is. All right, so we have substituted this over here. So what happens? Now we divide and multiply by mu 0. All right, on dividing and multiplying by mu 0, here this forms mu 0 square, and the divided mu 0 remains as it is. So now we set up a formula, because we know mu 0 n, we know mu 0 ni is equal to B. So this becomes half B square over mu 0. So mu B is equal to half B square over mu 0. This is expression for energy density stored in magnetic field. All right, so again I repeat, there are formulae which you have got to keep in mind. This is one formula, this is one formula, this is one formula. These are the formulae which you have got to keep in mind for your numerical purpose. Okay.